All right, let's jump right in. Today, we are tackling one of the most amazing connections in all of physics, the secret relationship between electricity and magnetism. For thousands of years, everyone thought they were two completely separate things. But it turns out they're really just two sides of the same incredible coin.
So let's frame this as a mystery. For basically all of human history, you had electricity, lightning, static electricity, and you had magnetism, that strange force that makes a compass work. And they seem to have absolutely nothing to do with each other. So what was the secret that was hiding in plain sight?
Well, our story starts with the very first clue. And the best part? It was discovered completely by accident, right in the middle of a university lecture.
To really get how big of a deal this was, you have to look at the timeline. For literally 2,000 years, these forces were just weird things that happened. Then, bang, summer of 1820, everything changes. It would still take a few more decades for the great James Maxwell to write down the final unified laws, but this was the moment the first domino fell. And this is the guy who started it all, the Danish physicist Hans Christian Ørsted. As the story goes, he's in the middle of a lecture, showing his students how an electric current can make a wire heat up. Pretty standard stuff. But on his table, just by chance, he also had a magnetic compass sitting nearby.
And then he saw something that nobody had ever put together before. Every single time he flipped the switch to send current through the wire, the compass needle, which should only ever point north, twitched. It moved. He turned the current off, and it snapped right back. A wire with electricity flowing through it could actually affect a magnet.
Ørsted's conclusion from this was just revolutionary. He realized an electric current is nothing more than a whole bunch of charges moving together. So he figured it must be the moving charges themselves that are creating their own magnetic field in the space all around the wire. That's what was pushing the compass needle.
Okay, so Ørsted proved a connection. But what does this new, invisible magnetic field actually, look like? Let's try to see it.
So imagine you could put a bunch of tiny compasses around a wire. And let's say the current is flowing straight out of the screen right at you. Look what happens. The compasses don't point toward the wire or away from it. Instead, they all line up in a perfect circle around it. They're literally tracing the shape of the magnetic field.
Now watch this. If we reverse the current so it's flowing into the screen, away from you, instantly, every single one of those compass needles flips 180 degrees. The pattern is still a circle, but the direction is completely reversed. This proves that the direction of the magnetic field depends entirely on the direction of the current. And this isn't just some neat drawing. You can see this for yourself. If you take a wire, run a current through it, and sprinkle iron filings around it, they will physically line up into these perfect concentric circles. You are literally seeing the invisible made visible, the shape of the magnetic field created by moving charges.
Okay, so a moving charge creates a magnetic field. Got it. But what happens if we flip the whole scenario around? What if a moving charge flies into a magnetic field that's already there?
For that, we have to talk about this man, the Dutch physicist Hendrik Lorentz. He took what Ørsted and others had discovered and put it into a precise mathematical formula that describes the force a charge feels when it moves through a magnetic field.
And this is his famous equation for the Lorentz force. It's a bit of a beast, but we're just going to focus on that last part, the magnetic force. It says the force depends on the charge, its velocity, and the magnetic field. But you see that little X symbol between the V and the B? That's a cross product, and that mathematical twist leads to a really, really weird kind of force.
So what's so weird about it? Well, this force doesn't push the particle forward or pull it back. It pushes it completely sideways. In fact, the force is always at a perfect right angle to both the direction the particle is moving and the direction of the magnetic field. To keep it all straight, physicists came up with a handy trick called the right-hand rule to figure out which way that sideways push is going to go.
But there's one crucial detail you got to remember. The direction of this sideways push depends on whether the charge is positive or negative. For a positive charge, like a proton, the force goes one way. But for a negative charge, like an electron, the force points in the exact opposite direction. The same field will push them in opposite ways.
So you've got this constant sideways push on a particle. What kind of motion does that even create? Does it speed up? Slow down? Nope, it does something much cooler.
Think about it. If you're always pushing on the side of a moving object, you can't make it go faster or slower, right? You can only make it turn. In physics terms, because the force is always perpendicular to the motion, it does zero work, and that means the magnetic force can never ever change a particle's speed. All it can do is change its direction.
So what happens when you're constantly changing a particle's direction but not its speed? You go in circles. If a particle enters a magnetic field at just the right angle, it gets locked into a perfect circular path. And if it comes in at a different angle, it makes this beautiful corkscrew shape, a helix. This is exactly what causes the northern lights. Charged particles from the sun get trapped in the Earth's magnetic field and spiral down towards the poles. A great way to think about it is like an invisible leash. The magnetic force is always pulling the particle sideways, tethering it, and forcing it to curve. This constant pull toward a central point is exactly what we call a centripetal force. It's the same kind of force that keeps the Earth orbiting the sun.
All right, we've gone from a big idea down to a single tiny particle. Now let's bring it all the way back up to something big enough to see and hold, a piece of wire.
So, picture this setup. We take a wire, and we just hang it in a magnetic field. We know gravity is pulling it down. But we also know that if we send a current through it, all those little moving charges inside are going to feel that sideways magnetic force.
And this is where we can actually defy gravity. Gravity pulls the wire down. Simple. Then we turn on the current, so billions of electrons start flowing. The magnetic field pushes up on every single one of those electrons. And if we get it just right, the total upward push from the magnetic force can perfectly balance the downward pull of gravity, and the wire just floats there in midair. This isn't just a cool trick. This fundamental force is what makes every electric motor on the planet work.
And this is real. We can do the math. To make a 200-gram wire float, you'd need a magnetic field of about 0.65 Tesla. That's the power of electromagnetism right there. The combined tiny pushes on electrons defeating the gravitational pull of the entire planet.
So we started with a twitching compass needle, and we ended with a levitating wire. And it all comes down to one incredible idea. Moving charges create magnetic fields, and magnetic fields push on moving charges. It really makes you wonder, doesn't it? If a connection this huge was hiding right under our noses for 2,000 years, what other invisible connections are out there, just shaping our world waiting to be found?